So let's get into lesson 2.5. We're going to talk about zeros of polynomial functions. Let's pray before we get started. Father, I thank you for this opportunity, and I pray for right now the person who's watching this video. I pray that you would bless them. I pray, Father, help me to explain the material in a way that's understandable, and I pray that it's retainable, and that you would help my student to work through the problems and to do the best that they can to understand the material. In Jesus' name we pray. Amen. All right, let's talk about the Fundamental Theorem of Algebra. It's a pretty simple theorem, but at the same time, there's a key phrase here, or a key word that we have to understand, and it's the word system. If f of x is a polynomial of degree n, where n is greater than 0, then f has at least one 0 in the complex number system. Now, in the past, I've had students that are a little bit confused of this theorem, and here's the reason why. Because when they read this theorem, they think that that means that every function is going to have a complex number that's a 0 of the function. But that's not necessarily true. That's not what it's saying. So, for example, let's take something very basic. So, f of x equals, let's say, x squared minus 9. Now, what are the zeros of this function? Well, there are two of them, x equals 3 and x equals negative 3. And both of these are real numbers. They're not complex numbers. So my students would be confused because they would say, well, these are real numbers, they're not complex numbers. But let's look again at what it says. It says that an f has at least one 0 in the complex number system. And so it's not that it's going to be a complex number, but that it's going to be something that's in the complex number system. So here's a graph of the complex number system, and notice that the real numbers themselves are inside of the complex number system. So real numbers are part of that system, and that's all the Fundamental Theorem of Algebra is saying, it's saying there's got to be at least one 0, that means a number that sets the function equal to 0, in that system, okay? All right. So make sure you read through that, understand that it's the complex number system and how that works. And we've already been working with the Linear Factorization Theorem, even though we haven't formalized it. It says that if f of x is a polynomial of degree n, where n is greater than 0, then f has precisely n linear factors of the following form. Some real number a sub n, times x minus some number c1, x minus c2, x minus all the way up to x minus cn, where c1, c2, all the way to cn are complex numbers. Now again, you got to remember that real numbers are part of the complex number system. Okay, so typically in the past, when we've done a linear factorization, we've dealt with specific real numbers, but we've expanded our idea of what a number can be. So, okay, note that the Fundamental Theorem of Algebra and the Linear Factorization Theorem tell you only that the zeros or factors of a polynomial exist, not how to find them, and such theorems are called existence theorems. You may get the thought that, well, that's kind of pointless if they're not going to tell me how to find them, but that's not true. They're actually very valuable, because if you know, for example, that certain zeros don't exist, I hate that bell, I really hate that bell. If you know that certain zeros don't exist, then you won't waste your time trying to find them. And so existence theorems can be very useful. Remember that the n zeros of a polynomial function can be real or complex, and it may be repeated. Okay, so here's some examples. Let's say I have f of x equals x minus 2. This has exactly one 0 at x equals 2, and x equals 2 is part of the complex number system. Multiplicity. Let's say I have x squared minus 6x plus 9. That's factorable. I can break that apart into x minus 3 times x minus 3. So this function has exactly two zeros, both of which are 3, and that's called a repeated 0. The third degree polynomial function, x cubed plus 4x, can be broken up into x times x squared plus 4, which can be broken up again into x times x minus 2i times x plus 2i. And so this function has exactly three zeros, 0, 2i, and negative 2i. the fourth degree polynomial, x to the fourth minus 1, can be broken up into x minus 1 times x plus 1 times x minus I times x plus I. And so this has exactly 4 zeros, 1, -1, I, and -I. So okay, at this point, I'd like you to pause the video, and I'd like you to go to exercise 9 and try and figure out exercise 9. Go ahead and do that. So here's number 9. It's already broken up into a linear factorization. Okay. So the zeros of this function are 0 and 6. And 6 repeats twice. So technically the zeros are 0, 6, and 6. But 6 has a multiplicity of 2. Let's talk about the rational zero test. The rational zero test relates the possible rational zeros of a polynomial. And so that word possible is what's important here. Having integer coefficients to the leading coefficient and to the constant term of the polynomial. Okay, so what this is going to do, we're going to read this, and I'm just going to tell you right now, after we read it, it's probably not going to make a lot of sense. It's when we start working it out that it's going to make a lot more sense, okay? But reading through it, making sure we at least try to understand it, is still important. So if the polynomial f is equal to a leading coefficient a sub n times x to the nth power plus all the descending terms all the way down to a constant, the trailing coefficient, a sub 0. Now if all of these a's here are integer coefficients, then every rational zero of the function f has this form, p over q, where p and q have no common factors other than 1. P is a factor of the constant term a sub 0, that's the trailing coefficient, and q is a factor of the leading coefficient a sub n, that's the very first coefficient. So to use the rational zeros test, you should first list all the rational numbers whose numerators are factors of the constant term and whose denominators are factors of the leading coefficient. Now, we just read through that. That's not going to mean a whole lot right now. And to make matters worse, I think that their example 2 is a horrible way to start off the whole process. They really don't do a good job, because example 2 shows how the zeros, this rational zero test, fails. And that's a horrible way to introduce the concept. So I'm going to first skip down here to example 3, and we're going to look at how the rational zeros test works. So, okay, the leading coefficient here is a 1, since this is x to the fourth, and the trailing coefficient is -6, since that's just the constant term. Now, technically what you do is this. You have to find all the integer divisors of -6, and you have to find all the integer divisors of 1. So what numbers divide into 6? Well, 1 divides into -6. -1 also divides nicely into -6. 2 and -2 divide nicely into -6. 3 and -3 divide nicely into -6. And finally, 6 and -6 itself divide nicely into -6. Now, because the leading coefficient is 1, this process is going to be dirt simple. In other words, all of the possible rational zeros will be all of the possible divisors of -6. That's what you get whenever the leading coefficient is 1. So what this is this is a list of possible zeros. That doesn't mean that all of these will be 0. So if you plug these numbers into the function, that doesn't mean that all of them you'll get 0. It just means that if the function has rational zeros at all, then they've got to be in this list. And the way that we go about finding out which ones are zeros is we use synthetic division. So we take the coefficients here and we place them into the synthetic process, and we're going to test one of these numbers. So I choose -1 and I place it here, and I run through the synthetic division, and lo and behold, I get a remainder of 0, and that means that x equals -1 is a 0 of the function, which also in turn means that x plus 1 is a factor of the function. So this function can be broken up into x plus 1 times 1x cubed minus 2x squared plus 3x minus 6. Now, once you've gone through the synthetic process, you choose either the same number again or a new number. They decided to choose the number 2, which is in this list. And then they went through the synthetic process again, and they got 1, 0, 3, 0. They got a remainder of 0, which means that 2 is also a 0 of the function. So now we can break this function up even further. We can break it up into x plus 1 times x minus 2. And now look at the coefficients here, 1, 0, and 3. So this is 1x squared plus 0x plus 3, which is the same as x squared plus 3. So because the factor x squared plus 3 produces no real zeros, okay, they're imaginary numbers it turns out, you can conclude that x equals -1 and x equals 2 are the only real zeros of f, which is verified in the following figure. In other words, those are the two places on the x-axis where the function comes through and hits through the x-axis. The other values, the imaginary values, which actually turn out to be plus and minus I square roots of 3, can't be graphed like that. All right, now I'm going to go back to example 2. All right. So example 2, let's find the rational zeros of the function here. Well, because the leading coefficient's 1, there's a 1 right here, the possible rational zeros are the divisors of this 1 here, which is positive and -1. Using the remainder theorem, I just plug in positive and -1, and I notice that I get 3 and -1, which is not 0. What's the conclusion? Well, the rational zeros test failed, and so I can conclude that the given polynomial has no rational zeros, which means it has to have at least one irrational zero. An irrational number is a number like pi, or the square root of 2, or the square root of 5, or the square root of 7. The rational zeros test can't detect those kind of zeros, irrational numbers. It's only as good as what the number is, and so if it's rational, then the rational zeros test will find it every time. But if a zero is irrational, well, the rational zeros test can't really do very much. Now let's try exercise 15. So go ahead and pause the video, and I want you to try exercise 15, and then we'll work it together. So okay, here's number 15. Let's make sure we understand the instructions. In exercises 15 through 18, use the rational zeros test to list all possible rational zeros of f. Verify that the zeros of f shown on the graph are contained in the list. So okay, let's look at the graph first. It looks like the zeros are 1, -1, and -2. The leading coefficient here is 1, and that means that the list should be only the numbers that are divisors of the trailing coefficient here. So in that list is +1 and -1. Those divide nicely into -2, and so do 2 and -2. So I get 4 possibilities. Well, looking from the graph, is 1 in this list? It is. Positive 1's right here. Is -1 in that list? Yes, it's right here, -1. And is -2 in that list? Yes, -2's in the list. The extra one that we have is +2. So again, this brings home to the point that what you're getting here are just possible zeros. It doesn't mean that they all work. It just means that if we find if there are any rational zeros, then they have to be in that list. That's all the rational zeros test says. Now I want you to try exercise 19 on your own. Go ahead and pause the video and do the best that you can, and then we'll go ahead and go over it. So okay, here's number 19, and number 19 says find all the rational zeros of the function. So first we're going to try the rational zeros test. The leading coefficient is 1. The trailing coefficient is -6. So that means all the integer divisors of -6 are potential candidates. So +1 and -1, +2 and -2, +3 and -3, +6 and -6. Now the actual answers are 1, 2, and 3, which are in the list I just gave you. But let me show you the process of how you would discover that. So let's move on to another. Let me show you the problem worked out. Alright, so here's a spreadsheet, and I've decided I'm going to use this to show synthetic division. And so let's see if 1, which was in the list that I gave, works. So we drop that 1, and so 1 times 1 is 1, so I put 1 here. I add these two numbers and I get negative 5. 1 times negative 5 is negative 5. I add these two numbers and I get 6. 1 times 6 is 6. And so I add those two numbers and I get 0, remainder of 0. And so that means that 1 was a 0 of the function. Now I'm going to run through the process again. This time I'm going to choose a different number that was in the list. And so remember, I had plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Well, let me just choose one right now I know that doesn't work. And so let's do negative 1, just to show you that it doesn't work. And so now I'm going to take these numbers here. I'm going to put this here thing at the bottom so that it looks more like the synthetic that we've been doing in class. There's 1. Negative 1 times 1 is negative 1. And so add these together, I get negative 6. Negative 1 times negative 6 is positive 6. And those two numbers add up to 12, which is not a remainder of 0. So okay, negative 1 doesn't work. So now let's try 2. Drop the 1. 2 times 1 is 2. Negative 5 plus 2 is negative 3. 2 times negative 3 is negative 6. And so negative 6 plus 6 is 0. And so what's just happened here is that x equals 1 works, x equals 2 works. So now let's show you that x equals 3 works. So I put a 3 here. I drop the 1. 3 times 1 is 3. Add them out, I get 0. And so what that means is that this function right here can be factored into, let me go ahead and write it out, x minus 1 times x minus 2 times x minus 3. If we FOILed that all out, we would get that function right there. Alright, life's been pretty nice up to this point because the leading coefficient has always been 1. What happens if the leading coefficient is not 1, as in this example, 2 and 3? Well, then what I have to do is find all of the integer divisors of 3 and all of the integer divisors of 2. So what are the integer divisors of 3? Plus and minus 1, plus and minus 3. And so that's what they mean when they say factors of 3 right here. What are all the integer divisors of 2? Plus and minus 1, plus and minus 2. And so that's what they mean when they say factors of 2 right here. Now what you have to do is you have to take all of the ratios. In other words, you have to take plus and minus 1 over plus and minus 1, which is plus or minus 1, and plus and minus 1 over plus and minus 2, which is plus or minus a half. Plus or minus 3 over plus or minus 1, which is plus or minus 3. And then plus or minus 3 over plus and minus 2, which is plus or minus 3 halves. And so this is the list of possible rational zeros right here. Doesn't mean they all work. It just means that if the function has a rational zero, then it's got to be in that list. So what do? We pick one. So we choose 1. Drop the 2. Let's begin the synthetic process, and we get a remainder of 0. And so that means that the function here at the beginning factors into the following: x minus 1 times 2x squared plus 5x minus 3. Notice the coefficients here. Well, I can stop the process now because we can factor a quadratic. You could keep going with the synthetic process, but there's no need once you get to the quadratic level, the second degree level. You can factor that. And so this factors into 2x minus 1 times x plus 3. And so the zeros of the function are 1, 1/2, and -3, which, by the way, all were in that list. So those are the zeros of the function. All right, pause the video. I want you to try exercise 25 on your own, and then we'll go ahead and work it together. So here's number 25. C of x is 2x cubed plus 3x squared minus 1. And what we want to do is we want to find all the possible integer divisors of -1 and all the possible integer divisors of 2. So the divisors of -1 are plus or minus 1. The divisors of 2 are plus or minus 1, plus or minus 2. So what we have to do here is we have to take all the integer divisors of -1 and divide them by all the integer divisors of 2. So positive 1 over positive 1 is 1. Positive 1 over -1 is -1. Negative 1 over positive 1 is -1, which we already got. And -1 over -1 is positive 1. 1 over 2 is a half. 1 over -2 is a -half. And we get the same thing again when we take -1 over these two here. So that means that the list of possible rational zeros is as follows. And so these are the possible rational zeros. Now we would run through the synthetic process, and any value that gives me a remainder of 0 is a 0 of the function. And it turns out that 1/2 will give me 0, and so will -1. And so that is the process of how you work it out. Find all the real solutions of -10x cubed plus 15x squared plus 16x minus 12 equals 0. The leading coefficient is -10, and the constant term is -12. So we find all the factors of -12, which are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. We find all the factors of -10, which are plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. This actually gives us 32 possibilities because we have to take the ratios of all possibilities. 1 over 1, 2 over 1, 3 over 1, 4 over 1, 6 over 1, 12 over 1, 1 over 2, 2 over 2, 3 over 2, 4 over 2, 6 over 2, 12 over 2, 3 over 1, 3 over 2, 3 over 5, 3 over 10, 4 over 1, 4 over 2, 4 over 5, 4 over 10, 6 over 1, 6 over 2, 6 over 5, 6 over 10, 12 over 1, 12 over 2, 12 over 5, 12 over 10. Gives us a lot of different possibilities. All right, now it says from figure 2.33, which I'm assuming they graphed somewhere. There it is. Okay, so they graphed it to kind of get an idea as to where the zeros might be. So okay, it looks like 1/2 might be a possible answer right here. It looks like the reasonable solutions would be x equals 1/2. That's the one on the graph that looks the most reasonable. It looks like it's halfway here. They say here that x equals -6/5 is a possible solution, but they didn't do a very good job. Well, maybe they did. This would be -1, right? And so this is just a little bit more than that to the left. So okay, -6/5 would be a possible solution. And x equals 2. Testing these by synthetic division shows that x equals 2 is the only rational solution. So we're going to get x minus 2 times -10x squared minus 5x plus 6 equals 0. This is going to come from the synthetic division part. Now, you can't factor this by normal means, so since it's the quadratic, you're going to use the quadratic formula. Using the quadratic formula gives us the other two zeros, which are not rational numbers, and that's why they didn't appear in the list when we did the rational zeros theorem. All right, let's go ahead and try exercise 31. Pause the video, try exercise 31, And that's going to conclude part 1 to this lesson. So go ahead and pause the video, and then we'll go ahead and go over the solutions. Okay, here we go. F of x equals negative 4x cubed plus 15x squared minus 8x minus 3. Let's make sure we understand the instructions. List all the possible rational zeros of f. Sketch the graph of f so that some of the possible rational zeros in part A can be disregarded. And then C, determine all real zeros of f. All right, let's go ahead and let's first find all the possible rational zeros of f. What are all the possible integer divisors of negative 3? Plus or minus 1, plus or minus 3. What are all the possible integer divisors of negative 4? Plus or minus 1, plus or minus 2, plus or minus 4. And now what we have to do is we have to make ratios of those. And so here is the list of possible rational zeros. Plus or minus 1, plus or minus 3, plus or minus 1/2, plus or minus 3/2, plus or minus 1/4, plus or minus 3/4. Now our job is to sketch the graph of f so that some of the possible zeros in part A can be disregarded. So we graph our function, and it looks like our function passes through 1, and perhaps it passes through 3. So let's try and calculate f of 1. Yes, I get 0 right here. So 1 definitely goes in. Let's go ahead and try 3. And 3 definitely works also. So both 1 and 3 work. So as I go through the synthetic division, we can find out what the other 0 is, which is somewhere around here, which may or may not be negative 3/2. Let's see what we get here. Okay, so according to our graph, 1 should work. So let's go ahead and try that. Drop the negative 4. 1 times negative 4 is negative 4. That becomes 11. 1 times 11 is 11. That becomes 3. 1 times 3 is 3. That becomes 0. It also looked like 3 worked, so let's try that. Let's drop the negative 4 here. 3 times negative 4 is negative 12. Add that, that's negative 1. 3 times negative 1 is negative 3. And so that works out. So we get 0 in the end. All right. So that means that the remaining factor here, this would become negative 4x minus 1 equals 0. That would be the remaining factor. Solve that for x. That would mean x equals negative 1/4. Should be where it crosses. Let's go back. Oh, I see now. So that's 1 right there. There's negative 1. I didn't see that when I said before. So yes, negative 1/4 is where it goes through, right there. And so those are the zeros of the function. We got them. All right, that's the end of part 1. God bless you, wherever you are today.